8 national conferences. His areas of interest includes infectious disease modeling, mathematical epidemiology and ecology, differential equation, and dynamical systems. Sir, we are very happy to welcome you to this section. I request Dr. Govind Prasad Shagu to kindly take over the section.
Okay, thank you, madam. Thank you, head of the department of mathematics, SRM Institute of Science and Technology, Kattankulathur. Am I audible properly?
Yes, yes. Yes, sir. Yes, sir. Please continue. Yeah, continue, sir. Continue.
Okay. So, thank you, everyone. Thank you, organizer, for inviting me. First of all, I would like to regret you all that due to some technical difficulty, I could not continue my presentation in my laptop. So there is a little bit problem because I had some programs written in MATLAB. I would have shared my screen, laptop screen, so that I could have shown you how the things are working. Okay, so here already I have put here the graph generated by those MATLAB Mathematica code in the slide itself. So we can see the things, and sometimes I've also included the codings for the those graphs. So let us move further. So as the talk of today is dynamical system using Mathematica. So dynamical system is a very one of the active branch of applied mathematics actually. It is also pure as well as applied mathematics. And the application area of dynamical system is almost every walk of life. For example, physics, from where somehow it's originated, in chemistry, in biology, in social science, everywhere. And nowadays, as we are going through the COVID-19 pandemic, so it is also relevant in this scenario also. So the different forecasting and control strategies that were estimated with the help of mathematical model, that is using dynamical system. So let us start. So before we start the dynamical system, let me say a few words regarding the programming software Mathematica. Basically, there are a few more similar softwares like MATLAB or Maple, but there are certain things which makes Mathematica special among those softwares. As far as Mathematica and Maple are concerned, they are very similar. So, so far as my exposure is concerned, Mathematica is very good, especially when you are handling with computations, which is a very high-level language. So initially, we should learn it carefully. Debugging is a little bit difficult, but as we go on, then it becomes sim-friendly. MATLAB is more suitable, especially for me in case of numerical simulation and plotting, etc. So okay, so that is actually not the open source software. We have to purchase that, subscribe that. Similar softwares are available. Other popular softwares are Python and R, but actually we have here going to talk about that Mathematica. Okay. So what a dynamical system is? So as the name suggests, dynamic. So a system which is dynamic in nature. So what does it mean by dynamic? That is not static. So anything, a system which changes with respect to change in time. Here, time may be anything that is independent variable. Following certain rules. So that is described as the dynamical system. So one of the ancient example is actually the three-body problem of, let us say, Sun, Earth, and Moon. Just by studying this three-body problem and solving the orbits, we can easily predict, say, lunar eclipse or solar eclipse. So with the accuracy even today in up to seconds. So that is one example, classical example of we can say dynamical system. So what is dynamical system? System actually actually the system moves with from one state to another state. So how to describe a dynamical system? So dynamical system is basically the mathematical version of a real world problem, which we study. So it has to measure a component is called a state space. State space is basically, it determines the value of state vectors. Means to describe a particular dynamical system, we need certain things. If we know those certain things, then we can easily describe that. So that is actually the state variable. So for example, in the case of, as I told, the sun, moon, and earth, these three body problems, if we know at each point of time the positions in the space of these three say states. So if we know these states, then we can easily predict the solar eclipse or lunar eclipse when they are collinear. So that is the state space. So state space actually consists of state variables by which we can completely describe the system. And the evolution, because the system is not static, it is evolving with respect to time. So that evolution is governed by certain fixed rule, what we call a function. So that is, we can say the current, which just gives the information from what will happen from the current state to the next state. So that is, these are the two components. Next slide, please. Next slide. So these functions also depends on various parameters as well. For example, a typical example of a state vector, if it is depending on more than one dependent variable, then that can be written like a vector x, which is a function of t, x1, x2. So right hand side is basically a function of this state variable. And how this right hand side actually changes, or how this x are that is given by some functions. That is given in terms of vector functions, let us say f1, f2, and fn, so on. So if we say describe the system, let us say three-body system, then there will or suppose it is possible to describe the dynamical system with the help of three state variables. Then it will be the x1, x2, and x3, and the corresponding there will be three functions f1, f2, and f3. So that the system of equation will govern the dynamical system under consideration. So depending on the values of state variable, that is xi, and the independent variable, that is t, dynamical systems can be classified into many categories. For example, if x is say continuous or discrete, or similarly time that is independent variable is continuous or discrete, the independent variable is that is single, that is or more than one. The function f is discrete or continuous or differentiable, and so on. So depending on the different scenario, a dynamical system can be described in a different way. So here we can see dynamical system, it can be either linear or non-linear, just depending on the function f. If all the functions f are linear, then the dynamical system is linear, otherwise non-linear. Similarly, autonomous means actually depending, if the f, the function f, that is the flow, does not depend on time t explicitly, then that system is autonomous, otherwise that is non-autonomous. Similarly, conservative, if the total energy that is conserved, that system is conservative, otherwise non-conservative or dissipative. Similarly, depending on the nature, okay, so these are the system. If you talk about the linear system, then the behavior, okay, so since we are actually a little bit late, so I will go through quickly these topics. Linearity, I hope every one of us know about the linearity system. So it is when it is called linear, if the with respect to addition and scalar multiplication, so if this additivity and homogeneity is satisfied, then that is the linear. So these are certain examples: fx equal to 3x, fy equal to 3y, then that is linear. Next, please. Next slide, please. Similarly, nonlinear, if it has a higher degree terms, then that is nonlinear. Next, please. So these are the few examples of linear and nonlinear functions. Next slide, please. Okay, so what is autonomous? So autonomous system of ordinary, initially I'm talking about ordinary differential equations, and later on I will talk about the discrete, that is difference equations. So we do not, so our autonomous system is a system which do not depend on the independent variable explicitly actually. It is, so we call it time invariant system. So that is, suppose at a time t, the value of state variables are xt and yt, and if we add the time t plus delta, then the time shift, that is x theta plus delta t, and y plus delta t. So that can be the situations. Here is some example, yt equal to txt. So this is non-autonomous, and yt equal to system b, that is 10xt, which is an autonomous system. So this can be easily verified. Next, please. So these are the there is a result related to the non-autonomous system, that every non-autonomous system can be reduced by suitable change of variable into an autonomous system. So therefore, explicitly there is no need to study the non-autonomous system directly if you want. So that is actually the relationship between the autonomous system and non-autonomous system. So this is just the derivations of that is with respect to the time and after the time t. So the system is autonomous. So next, please. Okay. Similarly, already I have explained about all these things. So the conservative system is a total mechanical energy remains constant. So that is no dissipation present. Non-conservative is dissipative systems. Next, please. Discrete system. So this is important. Here in the case of discrete systems, so the state variable, what is called discrete system, there is two possibilities. Whether the state variable x are discrete and the independent variable, what we call time, is discrete. So when we call it a discrete system, when the time is discrete, but the state variable is continuous. So this is called the discrete system. When both are discrete, then that is called actually the lattice kind of things. So here by the discrete system, we mean that the time is discrete, but the state variable is continuous. So as we can see from the second equations, that x at time k plus 1 equal to f of x of k. So that is, if we know the value of a state variable at kth time, then with the help of function f, we can calculate the value of function value of a state variable at time k plus 1. So here f function, which actually gives the transitions from kth state of state variable to time k plus 1th time. So that is basically functions from that is the space space to space actually. So that is actually the here the functions. For example, if f(x) of k plus 1 is equal to f of xk, then just by taking the compositions k times, so this x of k can be written in the form of f raised to the composite k times at x naught. So these are the some numerical examples. Suppose initial value is say 1 lakh, then if the value of function is like 1.03 times xk, then the value of xk can be evaluated like this. Continuous system. So in the case of continuous system, basically we deal with more than a strong condition than the continuous. Actually, we take mostly the differential system. So obviously, all the differential system are continuous. Also, there is a theory of dynamical system for say discontinuous or finite discontinuous systems. Okay, so here we will talk about the continuous, that is differential dynamical system. So if the function f is continuous, then that is actually the continuous dynamical system. So for example, vertical throw is described by this function, that is ht prime equal to vt and vt prime equal to minus g, where h is the height and v is the velocity of the body. So this is just the simple example, because the motion of say any object that is actually continuous, so that throw of some particle or object can be governed by this system of differential equation, which is a dynamical system. So when the reals are acting, the system is called continuous dynamical systems, and when the integers are acting, the system is called discrete dynamical systems. Here acting means in terms of independent variable. Next, please. Next slide, please. Okay. Then there is a more terminology, what we call the dimensions. So what does it mean by dimensions? So if the number of state variable is just one, that is with the help of single state variable, we can completely describe the system, then that is a one-dimensional system. If a system needs more than one state variables to describe, then that is called multi-dimensional system. So the example that is x at time k plus 1 equal to a times x at time k plus b. So this is actually the discrete single one-dimensional system. Here in the form of vector, we can say the multi-dimensional system. A is an n by n matrix, B is a constant vector. So it is an n-dimensional system. Next, please. Okay, we can quickly skip these portions. These are just the basic thing just for revision. So from the linear algebra, we know that A, B, C, then this is the matrix multiplication. Is next. Identity matrix, determinant, next please. Actually, I have included all these things to calculate it in Mathematica. Okay, just wait. So go back. Okay. So because we will be dealing with the operations of linear algebra. So how we input a matrix into Mathematica. So here is the one typical example. So here capital A equal to is an assignment operator, and with the pair of brushes. So we just enclose the matrix, and each row is again enclosed by pair of brushes, and the elements are separated by comma. So that is actually the way how we enter any matrix in Mathematica. And if we use the command that is the matrix form, then it is output is given just like what we can see here, which is visible in the form of matrix what we normally have in the book. So similarly, the Mathematica command for identity matrix is just the identity matrix. So any Mathematica command starts with capital letters, and always it has a square bracket at the end, and within that square bracket we provide the argument to the any functions. For example, if we are calculating the determinant, then within the square bracket we have to provide a square matrix like that. Next, please. So just dot is actually the command for a matrix product inverse I capital. That is the within a square bracket matrix A. That is the command. Similarly, for trace we have TR. For determinant we have capital D ET. These are the basics Mathematica commands. Next, please. Okay. Similarly, eigenvalues and eigenvectors, we all know that a non-zero vector mu is called eigenvector of matrix A if A mu equal to lambda mu. So that is actually the definition, classical definition. Next, please. So we get the characteristic equation using this determinant matrix. So there is a built-in function in Mathematica to calculate the characteristic polynomial or characteristic equation of the matrix. That is a characteristic polynomial itself. The command itself is a characteristic polynomial in continuation. Next. Okay. So when the system is these are actually all about eigenvalues and eigenvectors. So we can skip this. So next, please. So here we are dealing with how to calculate the eigenvectors. Okay. So, but why the question is why we are discussing all this? These are very basic things. So the advantage of this process is that through this process, if our matrix is diagonal matrix, so with the help of eigenvector, we can diagonalize a matrix, coefficient matrix A. And if the matrix A is the diagonal matrix, in the case of, say, look at the left-hand side, in the case of a discrete dynamical system, so it rises to the power k, a to the power k, and which is for a diagonal matrix, just the each element of diagonal elements raised to the power k. Similarly, for the case of continuous dynamical system, look at the right hand side, that is vector xk equal to a to the power k. So here we are calculating the a is actually the okay. So that is the differential dynamical system that takes of the form vector xk equal to matrix A raised to the power k times x vector x naught. X naught is actually the initial vector. Okay, next slide, please. So if we solve that the right hand dynamical system, that is dx dt equal to go back vector ax, then its solution is given like this: vector xt x naught, that is a vector, into exponential at, that is actually the matrix exponential. So what is the benefit of diagonal matrix again? So the matrix exponential of diagonal matrix, actually that is again matrix each of the diagonal element raised to the power e to the power lambda 1 lambda I times t. So that is the benefit of diagonalizing the matrix. Next, please. So the purpose of all this is here we have some typical example of calculating the eigenvalue characteristic equation, then eigenvalues and eigenvectors. So the purpose is basically we can separate the coupled system of differential equations with the help of these transformations. So once the coefficient matrix is diagonal, so we can mixed, that is the coupled system of differential equations, they becomes the uncoupled or independent. Actually, we can later on we can see that. Next, please. So to get the eigenvalues, we have directly the command eigenvalues of a for eigensystem. It gives eigenvalues as well as eigenvectors. Next, please. So 6.3 is here eigenvalues, just other. Okay, trace, we know all about trace. Jacobian is very important concept here, which is used in the dynamical system, differential dynamical system. So what does we mean by Jacobian? Suppose we have n-dimensional dynamical system, which is governed by system of first order differential equation. Always remember, dynamical system is always a first order system of differential equation. It may be linear, it may be nonlinear. It is not higher order at all. So if the system is higher order differential equations, then with the help of introducing new variables, we can always convert it into the system of first order differential equations. I will explain that later. Next slide. So that was just to go back, please. The formula for Jacobian matrix. I want to just explain the, okay. So this is the Jacobian matrix. Again, it is a very simple mathematics. That is for first function f1, del f1 by del x1, del f1 by del x2, and so on in the first row. So what is the benefit of this Jacobian matrix? Actually, when we expand the left-hand side, that is the system of n differential equations, through Taylor series about some given point, then the first terms, that is the linear terms, have the coefficient j, that is the Jacobian matrix. So this Jacobian matrix helps to linearize nonlinear systems, and in that way it helps to study the linearized version of nonlinear system. Next, please. Okay, so here we have some more technical terms. What is we call phase space. So what does it mean by phase space? Suppose to describe just for a say free fall of a particle. So to describe that, actually, what state variables we are needed? We just need the initial positions, and so we want to know at a particular point of time what is the position of that particle or that object. So for that, the required state variable is say xt, yt, zt. That will be the function of time. So phase space will be the set of all possible points which the state variable can occupy, can obtain. So that is actually the totality of the all possible values of state variable. That is called phase space. So for example, if we are dealing say with say human population in a single dimension, then as we know that human population can never be negative. So the phase space in that case will be the open interval 0 closed 0 to open infinity, like that. So similarly, in the case of two dimensions, we also call it phase plane. What is phase curve? A phase curve is actually a plot of solution of the equation of motions. So that is called phase curve. So phase curve definitely it depends on the initial conditions. That is, suppose in the case of free fall of the object, it depends what is the position of that particle from where we are dropping. So that is actually if we drop from some particular positions, then it will form a curve, and that curve in the space will be called phase curve. What is phase portrait? Phase portrait is basically plot of single phase curve or multiple phase curve corresponding to different initial conditions. So if we keep on changing the initial conditions and plot all the solutions in the phase space, then we get a number of curves in a single graph, we can say. That is called phase portrait. Next, please. Okay, so let us have an example of a phase portrait of a simple harmonic oscillator. So here, either in this form of spring or in the form of pendulum, suppose the simple harmonic oscillator is governed by the differential equations x double dot plus omega square x equal to 0. Here x double dot is second derivative of x with respect to time. What is x here? X is actually the displacement from the mean value. So the mean value is designated as x equal to 0. So that is actually the displacement. V is the velocity, capital A is the amplitude, and omega is the angular velocity. So angular frequency. So if we solve this system because it is actually a linear system of differential equations, second order linear system of ordinary differential equations, we can get its solution very easily. So here x will be constant time cos omega t, and v, that is actually the that will be minus omega time a sin omega t, that is actually the velocity, the derivative of x. So this is actually the classical way of working with the differential equations. That is, whenever we have a differential equations, we try to attempt to solve those differential equations to get a closed form solution of that differential equations. But in practicality, there are lots of differential equations whose solutions we cannot either determine, or sometimes we have to establish that whether the solution exists or not. So that is, in general, there is no formula till date, or possibly there will be no such formula to solve any nth order nonlinear differential equation. There is no general solution. So in that situations, we apply the techniques of dynamical system, and with the help of techniques of dynamical system, without solving exactly, that is in this manner, the differential equations, we try to get the properties of solutions. That will be the solution of the differential equation. So that approach is basically the dynamical system approach, and this approach originally coined by Poincaré, and so that is the dynamical system approach. Again, here if we rearrange this x and v, and we proceed, then we can see that the phase space. So here on x-axis we are taking x, and on the y-axis, that is the, actually it is a second order differential equations. If we take x dot, that is the dx by dt equal to v, a new variable, which is actually the velocity, then it becomes the system of two ordinary differential equations, first order ordinary differential equations. That is actually, it is a two-dimensional dynamical system. One state variable is x, and another state variable is v. Next, please. So here we will see the after rearranging the terms and adding these two equations, we get an equations, and which is nothing but an equation of ellipse. So what we get, that the trajectory or phase portrait of this simple harmonic oscillator is in the form of ellipse, where one coefficient is a, another coefficient is omega a, where a is the displacement. Next, please. Next, please. So this is the typical graph of this phase portrait. So here we have taken some numerical values for capital N omega. That is, A is taken as 1, omega equal to 10. Then if we start from initially from 1 amp, that is meter, initial velocity 0, then this is actually the phase space. Next, please. Okay, next, please. Okay, so here, as we see that, so ideally, the right hand side is actually the simple harmonic oscillator, that is the idealistic situations. So if we give some amplitudes, let us say 1, 2, and so on, and then that is actually the trajectory of the simple harmonic oscillator. But in practice, what will happen, that suppose in the case of a simple pendulum, if we give a little push initial velocity to the from the equilibrium, then due to the gravity and other frictions and other restrictions, it will be damped oscillation. So that is the second one. So initially the oscillation, that is, the amplitude is decreasing, and eventually it is merging to the 0, position, which is actually the position at rest. So we will study about this later. Next, please. These are the typical Mathematica commands to generate, to solve these nonlinear differential equations and to get the trajectory. So from this we can copy and sometimes it is not possible to copy and paste it in the image format. We can generate this. So on the first figure, what we see that this is with respect to the time. So this is just the oscillation. This is the in the case of simple harmonic oscillations. So the amplitude is equal all the time. Next, please. This is the damped one. Next, please. Okay. So the question is similar. The question is simple. What will happen if we disturb from the steady state at what we call equilibrium? So what does it mean by equilibrium in the case of simple harmonic oscillator? So the equilibrium is the rest positions. So at rest positions, that is when x equal to amplitude is a is 0. From the equations, we can see that the system does not change. If a0 initial velocity is 0, then the system does not change. So any point on the phase space, or that is actually in which the system does not change with respect to time. So that is actually called the fixed point or steady state. Steady state is the general term. So for example, look at the second paragraph. In the case of differential dynamical system, dx dt is equal to fx. If the fx is 0, then the derivative will be 0, that is the rate of change with respect to time will be 0. So when the rate of change is 0, so there will be no change with respect to time. Even though if we start from different initial condition, then the system will evolve, that will not remain fixed. So what is fixed point or steady states or equilibrium points? That is some special points on the phase space. If we start the system from that point, then the system will behave like a static system. So there will be no change unless we produce some disturbance or some perturbation or fluctuations in the system. So that x, that is a vector x bar here we can say, that is the special value, or x equal to x bar is a special solution of the differential equations at which there is no change. So how to calculate is numerically. So just f of x bar equal to 0, just solving this nonlinear equations, we get the x values of x bar, and that is actually the steady state or fixed point of the dynamical system. What is the meaning of stability? Stability means if we push a little bit or if we fluctuate a little bit from that point, that is x bar, then the system will remain again come back to that situation. So that is the stability. Just imagine the example of, for example, say three-body problems, and now in this case, Earth, Moon, and a satellite. So when a satellite is launched, so it has a stable orbit, fixed some stable orbit. What does it mean? That it will evolve on that orbit itself. So if there is a little fluctuations is given to the satellite, then what will happen? That is the questions. So the question is whether it will again, with respect to time, come back to its stable trajectory, or it will go away permanently from the stable trajectory. So that is the question, and this question can be answered for the dynamical system without solving the dynamical system, that is the system of ordinary differential equations. So that is actually the role of, and at the same time advantage of dynamical system. So there are certain equilibrium points which we call stable equilibrium point. So what is stable equilibrium points? So if we start in the neighborhood of that equilibrium point, x naught is taken near the neighborhood of x bar, then as t tends to infinity, so x will approach to x bar. That is, eventually the system will again converge to that will be remain in the neighborhood of the equilibrium point. Then that is called stable. What is marginally stable? So that is also sometimes asymptotically stable. So in limiting case, if it converges to the equilibrium point, then that is called asymptotically stable. Marginally stable, it means that that remains near x bar, that is the equilibrium point, but it never converges to equilibrium point. That is called marginally stable, or sometimes neutrally stable. And what does it mean by unstable? So if it goes away from that equilibrium point with respect to the fluctuations, due to the fluctuations, then that is actually called unstable equilibrium point. So similarly, what is an attractor? So for example, if we are throwing, if you want to study the throw of a ball, and what is the trajectory of the ball. So if we throw initial velocity, then there is some limitations. That is, if the initial velocity is limited, then the ball will come back to the earth. But if suppose the initial velocity is say greater than the escape velocity of the earth, then the ball will never come back to the earth. So what does it mean? So it means that is some similar, not exactly mathematical example of what we call basin of attraction. So what is an attractor? Attractor is basically those portion of the phase space. If we start from those attractor region, taking the initial conditions, then we will come back to the equilibrium point. So that region of the phase space is called basin of attraction, or that set itself is subset is of the phase space is called an attractor set. Okay, next please. So this attractor may be of different times. Perturbation is just a small change we apply to the system. Next please. So this is a example of situations. In the case of this is the in the phase space, the first stable. So if we start from various initial conditions, we are converging to the equilibrium point. Marginally stable, so we are not converging to second figure. So we are not converging to the equilibrium point, but we are also not going away from the equilibrium point. Third, that is unstable. So you can see the arrow indicates, so the beginning of the point, arrow indicates the upward trend. That is, if the initial value is taken by the tail of the arrow, I mean that this curve, then with respect to time, it will move in the direction of arrow. So here the dot is actually the equilibrium point. So what we see here, so if we see here that if we are coming to that equilibrium point vertically, that is through positive y-axis or say negative y-axis, then we are approaching to that equilibrium point. But if we are along x-axis, then we are moving away from that equilibrium point. So this is actually what is happening. We are approaching to the equilibrium point from some direction, but as we approach near, then we are moving away into another direction. A simple example is actually we can see say the back of a horse. So when we do the horse riding, so if we see from say left to right, from a rider's point of view, then it is initially increasing and then decreasing. And but if we see from front to back, then so that is from one direction it is like a minimum, that is attracting. From another direction it is repelling. Next please. So this is a typical example of say bacteria in a jar. So the population of bacteria in a jar is governed by dx by dt. See the equation in blue, that is Rx. So what is R here? R is B minus P, where B is the birth rate. Okay, let me read. Let B the birth rate, be relative rate of which bacteria reproduce, and P for pair is the relative rate at which they die. Then the growth rate actually that will be governed by R equal to B minus P, and that growth rate is R. So the differential equations, let us say, is governed by dx by dt equal to Rx. This is one-dimensional differential equation, dynamical system. So it's a closed form solution when the x at t equal to 0 is x naught, is xt equal to x naught times e raised to the power rt. So this is what we call the logistic growth model. So there are certain restrictions with respect to this particular solution. So what is the equilibrium point here? So dx by dt equal to Rx. Actually, I was going to use the writing pad with tablet, so I would have derived this, but due to some technical difficulty, I'm unable to explain that. So dx by dt equal to Rx. If we put Rx equal to 0, then we get x equal to 0. So the only equilibrium is x equal to 0. So the question is, what if we start near 0, what will happen? So definitely if R is positive, you can see that ht tends to infinity, so the xt will grow indefinitely. Similarly, if it is governed by another differential equations, dx by dt equal to bx minus px square, here the term px, basically, that is actually the competition by bacteria, so the capacity of the environment. So there is sometimes, if suppose it is produced in a jar, then a jar has a limited capacity to produce the bacteria. So there is a carrying after that certain level, so they will be fighting for survival. So that term is actually included in using the minus px square. That is actually the modeling techniques. I'm not going to explain that much right now. So in that situations, now the dynamical system is governed by dx by dt equal to bx minus px square. Here we can see from the right hand side. Now the differential equation is not linear; it is non-linear because of the term minus p times x square. So next, please. Again, we can calculate this equilibrium point. So if we equate the right hand side to 0, then we will get two equilibrium point. One will be x equal to 0, another will be x equal to b by p. So here, as we can see, that is actually the closed form solutions from using the Mathematica. You can solve such differential equations, simple differential equations. So here we have two equilibrium points, that is x1 equal to 0 and x2 bar equal to b by p. What does it mean? It means that if you are taking initial value of population, that is bacteria, equal to 0, then it will be 0 all the time, because the growth is governed by the right hand side of the differential equations shown on the top of this slide. So there will be no bacteria at all. And the second one is, if we initially, if time t equal to 0, the number of bacteria is given by b by p. So just substitute the value b by p in the right hand side of the differential equations, then definitely it is 0 because we have derived it from there itself. So the right hand side of the differential equation is 0. What does it mean? It means that dx dt is 0. What does it mean? It means that the net growth rate of the bacteria will be 0. What does it mean? It means that the level of bacteria will remain constant at level b by p. Although due to growth and death, some bacteria will actually will be reproduced and some bacteria will die, but the net number in principle will be same, that is constant all the time. So that is what is actually the equilibrium solution, what we call the equilibrium solution. So this x1 equal to 0, x1 bar equal to 0 and x2 bar equal to p by q, these are the two special solutions of the differential equations given on the top, and these are the called steady state solutions, or sometimes these values are called equilibrium values. Okay. Next, please. So now we are interested in explaining what will happen if we start the initial populations near these two equilibrium points. So the first fixed point or equilibrium point or steady state is x1 bar equal to 0. So what will happen if the initial population of bacteria will be very close to 0? So that is a small perturbation. So the question is, with respect to time, will it be 0 population in the jar itself, or will it grow up to the carrying capacity of the jar? So that is the question. So that can be answered through the we can have the closed form solutions. Please show me the slide back, please. There is a solution of this differential equation. So from there, you can see that as e to the power bt. So and so that is actually the situations. So the first is unstable. Unstable, how we can, so that if the growth rate is positive, that then from the result of the calculus, the population will be increasing. So that is the derivative of f function, right hand side function. If that is positive at the equilibrium point, then that will be the unstable equilibrium. And if the derivative of the right hand side is negative or have negative real part at the equilibrium, then that will be stable. So that growth rate will be negative. Next slide, please. Okay, so in this way, what we have seen here in the last example that we had two equilibriums, x1 bar equal to 0, x2 bar equal to b by p, x1 bar at x1, just 1 minute, go back please, then I can skip this second example. So here, okay, so the derivative, go back please, left one more, go back slide. I want to see the differential equations. Differential equations, okay, good. So from here, what is the derivative? B minus 2px. So just calculate the value of b minus 2px at x not x1 is not equal to 0 and x2 bar equal to b by p. So we will find that at x1 bar its value is positive, and at x2 bar its value is negative. Here we are assuming that both b and p are positive constant. So in this way, so that is actually the x1 bar is repelling, that is the unstable, and x2 bar, that is b by p, is stable. Next please. Next two slides. Next. Next. Okay. This is a typical example of prey-predator model. So R is actually the rabbits, that is the prey, and W is wolf, that is the predator. So wolf predates the that actually rabbits prey. So here the growth rate of rabbit, that is R dr by dt, is governed by E R times A is the actually the growth rate of rabbits. So here the terms G minus GRW. So that is actually R due to the interaction of R and W. So R is rabbit, W is wolf. So due to their interaction, here interactions means hunting. So the the growth rate of rabbits is decreasing, and that growth rate of due to the consumption of rabbits by the wolf, the growth of wolf is increasing. So that is, there is a, in the second equation, the term plus HRW. So G, what is the relationship between G and H? So H is less than G. Actually, this is conversion effect. And wolf is dying naturally with respect to natural death rate, that is minus BW. So this is a very classical example, what we call predator system. Next slide, please. So we can calculate its equilibrium points with the help of equating to right hand side 0 and get the various value. So if we see the page, this is the time series. The first graph is with respect to time. So blue graph indicates the rabbit populations, and red graph indicates the wolf populations. So what is happening initially? Look at initially, rabbit population is higher than the wolf populations, and then initially rabbit populations increases. But due to the increase in the hunting, rabbit population decreases, and due to the decrease in the rabbit populations, wolf populations doesn't get sufficient food, so wolf populations decreases, and due to the decrease in the wolf populations, rabbit population increases, and again due to the increase in the rabbit populations, wolf has sufficient food, so wolf population increases, and so on. So this is actually the cyclic or periodic behavior of the rabbit and wolf. So here the system is not stable, not hello? The system is not stably, but it is actually there is a periodic limit cycle. So right hand side is just the phase portrait. So on the x-axis, so in the first graph on x-axis we have on time. On the y-axis we have two populations, in blue rabbits and in red wolf. On the right hand side graph, this is phase portrait. On x-axis we have rabbit populations, and on the y-axis we have the wolf populations. So this is actually the attractor. So next please. So all this we can explore without solving the actual problem. So this is again for different scenario. Next please. Okay. So when extremely low rabbit naturally and low wolf mortality together with high wolf aggressively, both civilization will vanish. So initially, if so this is actually the different scenario. That is, if A is very small, 0.01, B is also small, G is small, H is small, and eventually what will happen? The population will be extinct. So this what we have. So okay, next please. We might have in the next slide the details. Okay. So basically what is happening, so we have in this case two equilibria. One is the 0-0 equilibria, that is the both the wolf and rabbit population will dies. Another is a non-trivial, both will coexist. And that non-trivial, that is non-zero equilibria is not stable, but that is actually oscillating about that equilibrium. So that is the case. This is the corresponding coding in the Mathematica. So these are just the solution of coupled order ordinary differential equations with initial conditions. This is basically the initial value problem and the solution. Next, please. This is the trajectory phase portrait. Next slide, please. Sorry, screen is gone, please.
Wait, sir, I will open the next PPT. Seeable, sir?
Okay. So here we will talk about topological classifications. Next slide, please. So what does it mean? We mean by actually topological classifications. Topological classifications means that basically we want to study the system qualitative. Qualitative means if the system, they say all the state variables are positive all the time. So that is one phenomenon. If some state variable vanishes, that becomes extinct, as we were studying in the last problem. So that is a different phenomenon. So that type of change in the nature of the solutions, so from being zero to non-zero, being connected to disconnected, that type of actually property, that is actually the topological property. Here we are going to talk. Basin of attraction, I have already discussed. So that is actually the reason in the phase space from where that's dynamical system from that reason that in taking initial conditions, then we will approach to the steady state solution. Trajectory, flow is basically the right hand side, the function of is called flow. What is null clients? Null client is actually the for each individual equations, if we equate right hand side equal to 0, so then that equation represents a curve in the space, and that curve is called null clients. Separatrix is basically the boundary. There is again a curve which actually discriminates the two different basin of attractors. Next, please. This is another example of simple pendulum, which is a dynamic. So here, phi represents the angular displacement, g by L. So the governing differential equation is given by phi double dot plus g by L sine phi equal to 0, where omega naught square equal to g by L. So g is the acceleration, gravitational accelerations. So if we take phi dot equal to omega, a new variable, so this is actually the angular velocity, then the first equations becomes the fourth equation, that is omega dot equal to minus omega naught square sine phi. So third and fourth equations that forms the system of first order nonlinear ordinary differential equations, and because sine phi is there, so it is nonlinear. So this is basically the two-dimensional nonlinear dynamical system. So if you want to calculate its equilibrium points, then from the first equation, that is phi dot equal to omega, we will get omega bar equal to 0. And from second equations, is sine phi equal to 0, we will get phi equal to n pi, where n is an integer. So there are so many equilibriums actually. In this case, there are infinitely many equilibriums. So the question is, what are the properties of those equilibrium? What are the properties of those equilibrium means? If we start from near any one of the equilibrium, then eventually what will happen? So that we need to understand, and we can get it. So since this is a nonlinear dynamical system, so how to solve that nonlinear dynamical system? So one way is to approximate with the linear one and study the linear dynamical system, and another one is directly handle the nonlinearity if possible and solve the system. So this is the corresponding Mathematica code. Next, please. And so this is basically what we call basin of attraction. So as I told, on the x-axis we have the phi, that is angular displacement. On the y-axis we have the angular velocity, that is omega. And what are the equilibrium points? So omega is always 0. So all the equilibrium points are on the x-axis, and they are n pi. So n pi it means 0, pi, 2 pi here, minus pi, 2 minus 2 pi, and so on. So the question is, what will happen to those equilibrium points? So here in this graph, as we can see, one equilibrium point is the origin, and through the this curves, we can see that origin is actually neutral. So if we start around origin, then we will remain so that is actually the basin of attractions. You can see that there is a separatrix. Separatrix is given by dark red curve, and so within that is the basin of attractions. Within the basin of attraction, it means that if we start with that much of angular velocity, then we will remain at origin in the long run. And but if we give the initial value, that is the displacement greater than n pi, then we will move to the another basin of attraction, and so on. So that is basically the different reasons. Next, please. So, these are the typical example when the angular displacement is 0. So that this is the equilibrium point. So no change will be there. The first situation. Second, initially we are giving 45 degree. So it is oscillating 90 degree, oscillating. Next, 135 degree. Next, 170 degree. Next. So up to 170 degree, actually we are again coming back to the stable fixed point 0. And if we go beyond 190 degree, then we do not come back to the that is pi. If we go okay, so we approach to the next equilibrium point. So that is the situation. 220. And see the last one, this is very important and to understand. If it is possible to keep the pendulum exactly vertical, then that pendulum will remain stable. Although practically it is not possible just due to our limitation that we cannot keep it exactly at 180 degree. But if it is somehow possible to keep it at exactly 180 degree vertically, then the at that mass, then it will be in stable conditions. So this is basically the another equilibrium which is unstable. So 2 pi, that equilibrium is unstable, 0 is stable. How you could calculate that, whether which one is stable or unstable? So in this case, we have two-dimensional situations, so we cannot calculate simply the derivative of right-hand side, and because it is non-linear. So we will study how to handle such situations in the next slides. Please, next slide, please. Again, suppose, but the earlier one is not realistic. Suppose there is a damped pendulum, so due to this, some friction or restrictions, then the basin of attraction will look like this. So what here we are getting actually, so if we start somewhere from the any red line, then we will be followed through that red lines. So the solution will be followed through that red lines, and as we can see here, that the origin is actually the basin of attractor. Next one, please. So this is the complete scene of okay. So the red one is basically the null lines. Null lines means the graph of f1 equal to 0 and f2 equal to 0. Dot are the stable equilibrium points. So we see that our center is stable, while the next equilibrium point, neighboring equilibrium point, that is pi and minus pi, they are unstable. So the basin of attraction is given in that particular trajectory is in a green color, stable manifold in the blue color, and unstable manifold in the green color. So what does it mean, stable and unstable? So you can see from the arrow. So here solid dot means stable equilibrium point, and hollow dot means unstable equilibrium point. Next, please. So these are all through the simulations. So this is the, again a simulation. So we can see how it is actually happening. So the damped pendulum, eventually it is converging to the equilibrium point, that is 0, 0, 0. Next one, please. Okay, so these are the mathematical conditions by which we can classify one-dimensional system as when it will be stable or unstable. So for the case of continuous, that means differential dynamical system, if the derivative is negative, then the fixed point is stable. If it is positive, fixed point is unstable. If it is 0, then we cannot decide directly with the help of this. Similarly, although we have not handled discrete cases, but in that situation, mod of f dash x bar, if that is less than 1, then is stable, greater than 1, then is unstable, and equal to 1, then we cannot decide. I will explain it later. Next slide, please. So these are the easy case for one dimension. Okay. How now you may be a little bit confused that how I am saying one dimensional, because originally the differential equation was one dimensional. Sorry, second dimensional. Then we have converted it into one dimensional. So I skip this example. Please next. Okay. So now we are going to talk about two-dimensional dynamical system. So now we have two state variable x1 dot equal to f1 x1 x2, which is actually actually it is autonomous. So no t on the right hand side. x2 dot equal to f2 x1 x2, and so if the right hand side we have the coefficient matrix A B C D. So that coefficient matrix is actually nothing but the Jacobian matrix, because already the system is linear. You can see the function f1 and f2 both are linear functions, and therefore the Jacobian is the coefficient itself. And then for this coefficient, that is Jacobian matrix J, we can calculate its stress and determinant, and the eigenvalue, the characteristic polynomial is given by the formula, the second last formula, that is lambda square minus stress of lambda time plus determinant of A equal to 0. From there, we get the eigenvalues lambda 1, lambda 2 equal to given by that formula. So the question is, all depends on the eigenvalues, because whenever we solve the coupled system with the help of, say, Jacobian matrix or generalized eigenvectors, then it becomes uncoupled, and it becomes e to the power lambda it. So it grows exponentially with the power of e, that is lambda it. So if all lambda I have negative real part or negative, then the system, the perturbations actually goes to 0, that the system becomes stable. And if one of the lambda I, that is the eigenvalue, is positive or have positive real part, then the system becomes unstable. Next, please. So the first example is attracting node. When both the eigenvalues are negative, that is a real number, -1 and -4, then the corresponding eigenvectors is 1, 0 and 0, 1. So we can transform this. Actually, already it is diagonal, so no need to do any transformations. So it is uncoupled one. So we can independently solve the first equation and the second equations. And since here we can see the closed form solution from the Mathematica, that is x10 is that is the initial value, e to the power minus t, and second one e to the power minus 4t. So since minus 4, these are the eigenvalues. So therefore, as t tends to 0, so this becomes e to the power minus infinity approaches to 0. And so that is actually the situations. So that is attracting node. So we directly approach to the equilibrium. So here we have phase portrait. We are starting from different initial conditions, and then we are approaching to the equilibrium point. Equilibrium point is obviously here 0, 0, as you can see from the equations. Just equate the right hand side to 0, 0. So we will get x1 0, x1 bar equal to 0, and x2 bar equal to 0. Next, please. So this is a stable fixed point. How to get the vector plot? So this is the typical example of vector plot without solving the differential equation, just using the right hand side, that is minus x1 and minus 4x2. So we can get the vector plot, and it also indicates that the equilibrium is actually stable. Next, please. So this is actually the mathematical theory. Here, repelling. Okay, eigenvectors directions are emphasized by black arrows. So in the case of real eigenvalues, so the eigenvectors are those vectors indicating the directions in the black. Next one, please. Repelling node. So repelling, as the name suggests, it is unstable. So one of the eigenvalue will be positive. Here both the eigenvalues are positive, and therefore it is a repelling node. So here repelling means at least one eigenvalue is positive. Node means all eigenvalues are positive. Next, please. So here we will see the graph. So we are moving away, even though we are starting very close to the equilibrium point 0, 0, but we are moving away with respect to time. Next, please. So this is unstable. Saddle point. So in the case of saddle point, one eigenvalue is negative while another eigenvalue is positive. So that along first eigenvector, it is stable. That is, it's tried to approach to the equilibrium point, but along second eigenvectors, it goes away from the equilibrium point. The figure, please. Next. So this is so here you can see from x-axis we are approaching to the equilibrium point 0, 0, but along y-axis we are moving away. Next one, please. So that is saddle point. Unstable. Saddle point is also considered as unstable equilibrium point or unstable fixed point. Again, source. Source means stable, and spiral. So when we call it is a spiral. In the case of the spirals, we have complex eigenvalues. So if the complex eigenvalues with positive real part, then it is repelling. If it has negative real parts, then it is attracting. So in the case of here in this case, it is a repelling spiral. So now it is going away from the origin, but it is not directly or say linearly going away, but it is going away through some spiral kind of curves. So that is an unstable fixed point. The spiral source sometimes called unstable focal point. It is also called unstable focal point. Next, please. Spiral sink. Sink stands for stability. Both eigenvalues are complex but have negative real part. So this is attracting. So this is converging to equilibrium point, but not directly linearly, but in a curvy manner. So this is a stable focal point. Next, please. Node center. When there is a marginally stable. So this is the case when both the eigenvalues are purely complex. So real part of eigenvalue is neither negative nor positive, but zero. So in that case, the equilibrium point is actually the marginally stable, that is neutral. So if you start from an equilibrium point, so that if you start from an initial point, that will evolve around that point. Okay. Next, please. So this is the summary based on the different eigenvalues. So from this new graph, you can see the values of eigenvalues. In the first one, the eigenvalues are on real axis with negative direction. So it is a negative real numbers. So then we have the source node actually, that is and so on. So we have explained all the things. Next, please. Stable star. So stable star is basically when it is stable. That means it has real eigenvalues with negative real part, and both are equal actually. So that is stable star. Is similarly unstable node when both are identical but positive. Next, please. Improper node with eigenvector. So when it is negative but two coincides, and that is we get only one eigenvector 1 0. So in that situations the situation solution is like this. So solution is not directly straight, but it is through that curvy manner. Next, please. And this is the summary of all of this. So based on here we have on x-axis trace of A, on y-axis we have determinant of A. So depending on different values of trace and determinant, that is P and Q, the value of lambda depends. So there are many reasons depending on the we have. So for example, the rightmost corner is unstable node. So for positive trace and positive determinant, there is both P and Q positive. We have unstable node if the value is right hand side to the curve, p square minus 4q equal to 0. That is the discriminant equal to 0, and so on. So this is just the summary of what I have already told. Next, please. And okay, so that last figure that was very important, because just to go back one to the back slide. Okay, so the next, yes, this one. So here, this is actually the case with the linear dynamical two-dimensional linear system. But this is not only the case with the two-dimensional linear system, but if the system is non-linear also, as we have seen in the previous example, we can linearize that. If we linearize a non-linear system, then the Jacobian matrix is actually the linearized one. And so this determinant A is actually nothing but the Jacobian matrix, and based on that Jacobian matrix, we can say whether those equilibrium points are locally stable, unstable, node, spiral, or what, saddle point, or what. So depending on the local behavior. So that is also the beauty of this dynamical system. That is, although we can sometimes it is not possible to see the long evolution in one, but we can say with surety what is the local property about some particular equilibrium point with the help of linearization. So linear system agrees with the nonlinear system in the neighborhood of equilibrium points. So that is actually a famous theorem of dynamical system theory. Next, please. Next. I'm skipping this example. This is the similar example. Next, please. This is the calculation in Mathematica. Next, please. Okay. So these are actually the results linearized for linear or linearized system. In the case of linearized system, the coefficient matrix is the Jacobian at equilibrium point. So all real lambda negative, then stable, and so on. Next, please. In the case of 3D, that is a 3D and higher dimension. So if all eigenvalues have negative real parts, then that is attracting node, see the left hand side. And if all have the positive real part, then that is repelling node, like right hand side, and so on. So these are quite similar as of two-dimensional system. But in this case, we have to see the all the eigenvalues. If all eigenvalues have negative real parts, only then the system is stable. And if at least one of the eigenvalue is positive, then the system is unstable. It may be saddle if some are positive and some are negative. Next, please. So saddle points, that is attracting in two directions, the left hand side, and repelling in one direction. In the right hand side, repelling in two directions, attracting in one direction, depending on the values of eigenvalues. So these are further stable focus node and so on. And the conditions are given. Next, please. Conditions are similar to that of two-dimensional system. So we will not discuss in details much about all these things here. So next, please. Next slide, please. How much time I have? Okay, 30. It is 12:30. Hello.
Hello.
Wait, ma'am. I will open the another file.
Okay, okay.
Okay, so since we started a little bit late, so I will quickly go through this nonlinear system. So in the second presentations, we talk about linear system. So let us see the nonlinear system. Next slide, please. So the question is basically how to deal with those equilibrium points. What are the nature of those equilibrium points? So how we do linearization? So that one of the method is actually what we call the first Lyapunov method of linearization, etc. So here you can see the Taylor series expansion. So if we neglect the nonlinear term, that is the higher order terms, then the function fx is approximated by fx bar plus del f by del x times x minus x bar. So if we see this in the matrix format, and that is the matrix version of Taylor series expansion, then since x bar is basically the equilibrium point, so f of x bar will be 0, and therefore fx equal to that is just the, so on the right hand side we will have the Jacobian matrix. Del f by del x is basically that becomes the Jacobian matrix into x minus x bar. So earlier in the original version, the equilibrium point was x bar, but in the linearized version, now the equilibrium point will be shifted due to the change in variable x minus x bar to the origin. So in that situation, so the next slide please, the linearized system will be dx by dt equal to ax. So that will be the linearized system. So that is just the original system and linearized system. Next, please. So it will, next slide, please. So this is just the coefficient matrix actually. So here we can see through the example. So let us have two-dimensional non-linear system. So since in the first equations x1 dot equal to x1 square plus x2 square minus 1, so clearly it is a nonlinear system. So we have the f1 and f2 equal to 0. So the solution of this will give us the two fixed points. So first fixed point is given by approximately in decimal 0.7.7. Then second one is minus 0.7.7. So these are the two fixed point of this equilibrium. So the question is whether the fixed points, what are the nature of those fixed points? So fixed point means these are actually the solution of this differential equation in a linear way, linearized system. So for that, we need to calculate the Jacobian. So for function f1, that is x1 square plus x2 square minus 1, we can calculate its derivative with respect to x1. Just see the equations on the bottom of the slide. So here we see that the del f1 by del x1 equal to 2x1 and so on. So these are the four values. Next slide, please. So putting these four values in the formula of Jacobian, we can calculate the Jacobian. This is the vector plot. Next. So from vector plot, you okay. The area around the, actually we have plotted the vector plot and now we are zooming in some sense around the equilibrium point. So we are just given the name to equilibrium point x a bar and x b bar. Then just see from the vector plot that x a bar is a saddle point because it is attracting in one direction and repelling in on the other direction. From the vector plot we can see that the x b bar, that is the second equilibrium point, that is actually the spiral sink because it is converging towards the arrow, the direction of the arrow is towards the equilibrium point. So this is from the simulation we can say using the mathematics. Next slide, please. And so that is the Jacobian df, 2x1, 2x2, 1 minus 1. And for this Jacobian matrix, we have to calculate its eigenvalues. And eigenvalues, so the eigenvalues are 1.90 and so at one equilibrium point. So at first equilibrium point, that is x a bar, the eigenvalues are one is positive, another is have negative real part and negative in fact, so therefore it is a saddle point. For the second one, the eigenvalue is actually complex but having the negative real part, the one minus 1.2071 plus minus 1. So that is a negative real part. So therefore the second one is a source, that is a stable, and it is a stable here, and that is actually the, okay, this is not node. So these are again the examples of few nonlinear systems. So here x dot equal to v and v dot equal to minus x minus mu v q. Here there is one important change in this model and the previous models, and that is just the introduction of the constant or parameter mu. So in the earlier case that was absolute constant, right now it is a parameter. That means depending upon different situations the value of mu may vary. So it is more interesting that the solution that is equilibrium as well as the stability will depend on mu. So for this we calculate the equilibrium point. So this is nonlinear system because of VQ. So first we linearize it and we calculate the equilibrium point. So first from first equations v bar equal to 0 and from second equation x bar equal to 0. So for although this is nonlinear, but 0 0 is the only equilibrium point. Now we want to know that what is the nature of the equilibrium point or the steady state solution, x bar equal to 0 and v bar equal to 0. So that we can do with the help of Jacobian, calculating Jacobian matrix around 0 0 and the eigenvalues of that Jacobian matrix. Next slide, please. And that can be confirmed with the help of numerical simulations. So that is DF, that is the Jacobian matrix, and if we put the value 0 0, then we get 0 1 minus 1 0. So what we see here that the eigenvalues are plus minus I. So that is real part of the eigenvalue is 0 and there is no negative part. So as we see that we have for mu equal to, okay, so that is the, so in that situation it will be neutrally stable. So if we increase the value of mu, if we increase the value of mu, then the value that is actually the different situations, that is the existence of what we call limit cycle. So here you can see that there is a curve that is around origin, and the trajectory cannot cross that curve. Okay. So next tool is actually the Lyapunov functions. Next slide, please. So for nonlinear systems, we can calculate the Lyapunov functions to study the nonlinear system. So Lyapunov functions is actually the concept is similar to the energy. We consider it in the form of energy, and we construct a function Vx. X is here the state variable, and if we construct a function Vx such that it is continuously differentiable around the fixed point, and it is positive definite. There is a Vx is 0 for all x, non-zero x, and okay, and its derivative is negative definite. That is dv by dt must be strictly less than 0 at all x, and if these three conditions are satisfied, then it gives the guarantee that the equilibrium point x star will be stable. So this is basically the method for stability of the nonlinear system. Earlier, the Jacobian method is just the we don't consider the nonlinear part. Here, in this case, Lyapunov method case, we consider the nonlinear portion part also, and we say that the x bar is actually stable. This is the nonlinear stability analysis. Next slide, please. So another example, the total energy of harmonic oscillator. So that is given by kinetic energy and 1 upon mv square. So at m equal to 1, k equal to 1, this is the E, and if we take E as the function V, then we can see that this is always positive definite, and its derivative. Here we will use the help of dx by dt and dv by dt, and we find it that it is negative, and therefore it satisfies all the three conditions of Lyapunov functions, and therefore the equilibrium point is stable here. Next, please. Okay. So at the fixed point, which is a conformity with the third conditions, okay, we can notice that it is always negative. So these are explained. The final conclusion is that the fixed point 0, 0 is stable. Next one, please. So that is a very tough question, how to estimate the Lyapunov functions, because there is no standard idea. So there are some hints. One way is just constructing the Lyapunov functions be like this. Next, please. There is in the form of product, but it is not guaranteed that it will always work. Okay. So that is the Lyapunov stability. Next, please. Asymptotical stability. We have talked about the asymptotical stability. This is for the generalized system. So we will not go much details, but as we can say that if x bar is the equilibrium point is called asymptotically stable if this condition is satisfied. That is mod of xt minus x bar t that approaches to 0. That is the solution approaches to the equilibrium point as t tends to 0 for all x naught element of V. So that's V is basically the basin of attraction. That is the neighborhood of x bar. Next one, please. Exponential stability. Now, next one. If it is less than some exponential function, then that is called exponential stability. That is just the technical term. Next one, please. Bifurcation. Bifurcation is very important. What does you mean by bifurcation? So, as the name suggests, bifurcate means actually breaking into two or more than two parts. But basically, bifurcation means actually the change in the qualitative or topological property of the solution of the dynamical system. That is called bifurcations. So, how the property can change either by removal of steady states or by the emergence of steady states, that is fixed point, or by switching of stability, that is one equilibrium point which is earlier stable was unstable, or which was earlier unstable was stable, like that. So there are two types of bifurcation we can call local bifurcation and global bifurcation. So local bifurcation basically depends on one single parameter, and global bifurcation is actually that does not depend on the some parameter. Next, please. I will explain it with the help of examples. So now we just see the example of logistic equation. This is actually the discrete dynamical system. So what happens in the discrete dynamical systems? Now the time is discrete. So instead of taking t, so now that is denoted by n, and n starts from 1. So that's the initial time. We can also start from 0. That doesn't matter much. So the here the equation is governed by xn plus 1 equal to r xn times 1 minus xn. So the right hand side is basically, it is called basically the logistic equations or Warhurst equations, and that right hand side is basically the flow or fx in the what we have studied in the differential dynamical system model. So how to calculate the equilibrium? So equilibrium in this case will be when the there is no change in the solution. So that means xn plus 1 equal to xn. So if we equate the equations, if we replace xn and xn plus 1, all the xi with the x bar, then we get the equilibrium solution. So the formula will be f of x bar equal to x bar. So solving that, we can get the equilibrium. Next, please. So these are the typical numerical values for different values of r. Next, please. So just wait, go back, please. So go back. So here we can see that if we take r equal to 0.5 and we start from the first column 0.5, then with respect to each iterations, that is x1 is 0.5, then x2 is 0.125, and from switching from x1 to x2 is x2 equal to f of x1, and f of x1 is given by here rx equal to 1 minus x. So we have the values of r here. So that is, so ultimately you see here that they are eventually after few iterations they are approaching to 0. In the second column for r equal to 0.8, it is approaching to again 0, but it has not approached yet, for and so on. See the third last column, that is r equal to 3.2, written in bold blue font. So here we will see that the value in blue, that is 0.7995, and then 0.5130. So we see here that these values are repeating actually. So this is actually the periodic point. Okay, so I will explain it this with the help of example, and if needed we will go back again on this slide. Next, please. This is the typical bifurcation diagram of logistic model. So what is actually plotted on x-axis and y-axis here? So on x-axis it is r. Remember the equation. What is the our evolution rule? X of k plus 1 equal to r xk times 1 minus xk. So that is the governing equations. So if we take r, so here on the y-axis, what we have here? So here we have population x. So that is, and we are not just plotting all the values. Just see the caption of the graph, that is and 300 iterations were calculated for every r. So initial value we always keep fixed, that is 0.01, and we iterate up to 300 points, and we plot the last few points. Let us say out of 300 we plot just last 50 points, then that per r versus those points of x. So that is, so up to 0.3, up to 1.0 to 3.0, that is the value of r, we see a single line. What does it mean? It means that the equilibrium, which is non-zero equilibrium exists, and that is stable. And after that point 3.0, so that non-equilibrium points become unstable, and a period doubling point occurs, as I explained in the table. So by the blue numbers, so x1, so f of x1 equal to x2 and f of x2 equal to x1. So that is actually toggling between the two numbers. So in that case, if we plot the last 50 number also, then we will get only two values, and those two values are plotted against r. So that is up to the point somewhere before 3.5, and again in that 3.5, each of the two values are again bifurcated into two. So So this is actually called period doubling route to bifurcation. So as we go further, that is, as we increase the value of r further, so this process becomes very rapid, and after certain times we see that there are some sort of all values in the range of 0 to 1 which we get in that iteration of 300. Next slide please. So this bifurcation diagram is very important. Next slide please. So extinction, so here these are explained. So for r less than 1, extinction means eventually the system, that is the x becomes approaches to 0. For r in between 1 and 3, so fixed point is stable. If we take oscillation area for r in between 3 to 3.57, so the series jumps between 2 or more discrete states, that is periodic orbits. And for 3.57 to r, so actually there is no definite order. So the higher values of r, that is greater than 4, so solutions zoom to infinity and the modeling aspects of the become useless, because almost all values in between 0 and 1 are assumed by the state variable x, and that also looks like random, although it is not random. Next one please. So this is the root of chaos, what we call chaos. Chaos is nothing but it looks like randomness, but it is not random, but it is actually sensitive to initial condition. Sensitive to initial condition. Even a small difference in the initial conditions will vary significantly in the long run. So these are the analytical calculations. So fx equal to x, that will be the formula. See the first equations for calculation of fixed point. So just solving these equations, this is called quadratic equations. We get the values of x1 is equal to 0 and the x2 is equal to 1 minus 1 upon r. So since it is a first one-dimensional discrete system, so if we calculate mod of fs f prime x bar, that is the derivative at x states, and that is r minus 2rx at x bar x1 bar. So for these 2 points we will calculate the value. If it is less than 1, then that is stable. If it is greater than 1, then that is unstable. So here we see that if r is less than 1, then so for x1 bar equal to 0, so the derivative is simply r. And so if mod of r is less than 1, that is r is always positive, so r is less than 1, then the origin, that is x1 bar is equal to 0, is stable. And if r is greater than 1, then it is unstable. And in between r, so for x2 equal to 1 minus 1 upon r, if we calculate the derivative at x2, then it becomes 2 minus r. So until 2 minus r's modulus is less than 1, it is stable, otherwise it is unstable. So in between 1 and 3, the values of r is the second equilibrium point, that is 1 minus 1 upon r, is actually stable, otherwise it is unstable. Next please. So there are certain kind of bifurcation, saddle node bifurcation, period doubling bifurcation, what we call flip bifurcation, pitchfork bifurcation, transcritical bifurcation, home bifurcation, and so on. Next please. These are local bifurcations. So I will go very quickly. So what is actually happening here? So this is just one-dimensional differential equation, r plus x square. So we get two equilibria. One is so here stable and unstable at x1 bar equal to minus of under root of minus r. If r is negative, then this is real, and so on. So at a time, one is so there are, if r is positive, so in that situations there are no fixed points. So when r is negative, then we have fixed point. So just see the is on the graph, so that is in the middle. So that is just on the vertex of this parabola. So that is for a positive value of r, there is no fixed point. For negative values of r, there are two fixed points given by x1 and x2. One is positive, one is negative, and out of these two, one is stable, another is unstable. So this is called saddle node bifurcation. Next one, please. So in the saddle node bifurcations, as the parameter increases, actually the equilibrium disappears. This is the two-dimensional one. In this case, one eigenvalue is negative, and another eigenvalue is positive. Just class here. Okay, this is the linearized version, saddle node bifurcations. Okay, this is the example of next slide, please. Period doublet or flip bifurcations. So here, what we see that this x n plus 1 equal to r x n the logistic equations. And so now, if possible, if we let r to be negative, so in the case of populations, it is not possible, but in other cases, it may be possible. So we can see the bifurcation diagram for both the directions. So for r negative and for r positive, the bifurcation diagram is here. We can plot the bifurcation diagram. We have the code for that. Pitch fork, as the name suggests, it is like just a fork. So we can see initially there is a single stable equilibrium up to the point say r equal to 0, and then two more equilibrium emerges. That is the two non-zero equilibrium emerges, and one becomes unstable while the other becomes stable. Here, stability is denoted by blue curves. So that is attracting, and red one is actually the repelling, and the solid line is basically the existence of stable equilibrium, and the dotted line is actually the unstable equilibrium. Next one. So subcritical case. So that was just the reverse of the supercritical pitch, when it is also pitch fork. So initially we have a stable one, and the other two non-zero are unstable. While the next round, okay. So next, this is actually the x equal to 2 unstable fixed points. Next one. Transcritical bifurcation. This is actually switching of the stability. So here always we have two equilibrium. One is 0, that is along x-axis. Another is non-zero. So one is actually earlier 0 was stable, non-zero was unstable, but after r equal to 0, the stability switches, and so the 0 equilibrium is unstable and non-zero equilibrium becomes stable. So this is called transcritical bifurcation. Next one, switching of stability between the two equilibrium points. So this is the Hopf bifurcation. And what is the Hopf bifurcations? Basically, a single fixed point changes into a limit cycle, or vice versa. In the first case, it is called supercritical, and the later case, it is called subcritical. So a single fixed point becomes, earlier it was stable, becomes unstable, and it produces a limit cycle. So let us see the example. So here we have the two nonlinear dynamical systems given by two equations, dx1 dt equal to the right hand side, and so on. So here we see that the only fixed point for this, that is equating to right hand side equal to 0. So that is x bar equal to 0, 0. Jacobian matrix, that is the linearized one, is given by df, and at x bar, so we have r minus 1, 1 r. So that is actually the next slide, please. So if we see the eigenvalues, then that eigenvalue is given by r plus minus I. So if as soon as r is negative, then that is stable. But when r is 0, then we get neutral plus minus I, that is neutrally stable. And when r is positive, then it becomes unstable. So for r equal to 0, so okay, so these are the typical simulations for different values of r. So in the first case, we see that the origin is stable. In the second case, that is r for r equal to minus 0.1. In row wise, in the second case, r equal to 0, so there is an emergence of limit cycle around origin. That is, origin becomes unstable. In the third case, the limit cycle that is r equal to 0.1, the size of limit cycle increases, and so on. So in the third case, that if we start from outside, then it will converge to the limit cycle, and if we start from the inside, then also the limit it will converge to the limit cycle. So here we see that the emergence, this limit cycle is actually the convergence. That is actually the convergent limit cycle. So it means that the converging solution is not necessarily to be a fixed point. So for example, as we talked in the first initially, that the three-body problem of say solar system, so that is stable, so that the path is not necessarily a fixed point, but it is some orbit. So that orbit is stable. So if there is a little bit perturbations, then with the respect to the time, it can adjust itself and converge to the equilibrium. That is again some orbit. Next one, please. This is the interpretation of 3D interpretation of the Hopf bifurcation. The limit cycle increases as we increase the R. In this case, the amplitude of the oscillation increases. Next, please. This is the corresponding simulations within the Mathematica. Okay. So these are the some general conditions for saddle node or Fitch-Fogg bifurcations, period doubling bifurcation, or Hopf bifurcation. So this is just the symbolic demonstrations when the real, actually the image is in between the real part and imaginary part of the eigenvalue of Jacobian matrix. And if the eigenvalues crosses through left hand side to right hand side, see the right upper graph for Hopf bifurcation, that if it crosses the imaginary axis from left to right, then the stability loses and there exists a limit cycle kind of things. In the discrete version, the lower side, okay, so this is actually the different versions of, in the case of period doubling, that is given for the discrete dynamical system. So when the value of eigenvalues, the magnitude of eigenvalues goes beyond mod 1, then that situations along the real axis, then the period doubling bifurcation occurs in the discrete dynamical system. So these are the conditions summarized in the form of the graph between the real and imaginary part of eigenvalues of Jacobian matrix. Next one, please. Last one.
टंकी जो बनाया था ना आपके
अभी बाहर से वो चल रहा है.
ठीक है चलो तो मैं आपको बता दूं.
Okay, hello.
Is the lecture over?
Yeah, I think
Another file will be.
Okay, no problem.
If you want, we can stop here. We can have a question answer session if the time permits. Otherwise, I can continue. No issue.
What about this audience? Would you like to have any questions? Would you like to ask any questions? Adityan, any questions from your side? Adityan is there?
Sir, Radhakrishnan is there, sir. Adityan is not.
Okay, what about Radhakrishnan? Any questions from your side? Radhakrishnan?
Sir, whether close, we have to close
Okay.
the
No,
session?
not like that. Expert sir is
Oh.
asking any questions, ask, like continues, or you will ask him to continue for another 5 minutes. Okay?
Okay,
Or
sir.
you can continue for another 5 minutes, sir.
You can continue, sir.
Okay, just I will summarize the things. So basically, just quickly go through some. Next slide, please. Okay. Next. Next. So these are the glimpses of actually the discrete dynamical system. Next. Keep on moving. I will stop you. Next, please. Okay, so one of the I can talk like directly. So there are certain special cases, as already fractals have been covered in this actually faculty development programs. So that is also some sort of dynamical systems, basically self-similarity kind of things. And there are n number of examples where the dynamical systems are applied. And so this is still very recent. I mean the hot research area from the application point of view also and from the mathematical point of view also. Sometimes few new physical situations actually gives a challenge to mathematicians to develop a new theory to solve that particular problem. So that is actually the dynamical system theorem. There are various aspects. If the number of independent variable increases, then that becomes actually partial differential equations and so on. If time delay is involved, then that is actually the delay differential equations. If and so there are a number of varieties of dynamical system. If stochasticity is involved, then that becomes the stochastic differential equation and so on. Okay, next, go to the second last slide. Second last slide.
So this one?
No, next, please. Next. I think I told second last, not first. Okay, towards the end. These are the Mandelbrot set. Keep on, okay, Julia sets. Okay. So please stop at the reference.
Yes, sir.
Go ahead. Stop at the reference. Differences. Next. 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 You are moving backward, I think. You are moving backward. Go ahead. Okay, fine. So with this, actually, I conclude. Thank you very much for patience, and again, sorry for inconvenience due to some technical issues. So just the last slide before thanks. I just wanted to show a good literature. If anyone interested in this field, okay, this one, stop. They can go through these books. These are very good books. So it is a dedicated book using Mathematica or MATLAB also, the dynamical system with applications between Mathematica and MATLAB. Another good book is by Steven Strogatz, the professor of Cornell University. And so, thank you very much. So, okay, you can refer these books. Thank you.
Sir, how do you get that? You had one cobweb graph. How do you get that?